The third example is the integral of 1 divided by x minus 1 from 0 to 3. Now, for this function, if we just evaluate the values at the two endpoints, then f0 will be equal to 1 over negative 1, which is negative 1, and f3 is equal to 1 over 3 minus 1, which is equal to 1 over 2. So there are no any problems for the endpoints of this function. Then without considering any availability of a vertical asymptote in between, if we just evaluate the integral, then it will be now you can see you have the new derivative of the denominator in the numerator, so you can just write it as x minus 1. Okay, so if you substitute the this upper and lower limits directly, then it will be ln2 minus ln1. That means it is equal to ln2, right? But there is a very big issue with this calculation. The reason is, as we consider the range for the integral as 0 to 3, right? Since this range is 0 to 3, and since our function is 1 divided by x minus 1, you can clearly see that for a point in between 0 and 3, precisely it is 1, for this point which is situated in between 0 and 1, the function will have a vertical asymptote. Okay, so if we do the calculation like this, that means we have not considered this existence of the vertical asymptote. So we must consider the existence of vertical asymptote to do this problem. Now, okay, so that means the third problem will falls under the third part of the theorem that I mentioned earlier, right? See, f has a discontinuity at c, where c is in between a and b, and a is the lower limit and b is the upper limit. So according to the example that I mentioned, a will be equal to 0, b will be equal to 3, and c will be equal to 1. So what we have is this function. Okay, that means what we should do is we should separately compute these two integrals starting from 0 to 1 and 1 to 3. So we should compute these two integrals separately, and if both these integrals converges, we can write down the equation by combining the two. And if at least one of them diverges, we can directly say that the total integral will also diverge. Okay, so that should be our goal to compute the given integral. So we'll first evaluate the integral from 0 to 1. So if you compute the first integral according to our rule that we described, that is by considering the left endpoint, I mean the left limit, because we are approaching 1 from the left hand side, then you can see now we have the same computation as before. We have the denominator and the derivative of the denominator in the numerator, so you have this relationship, and then you can see by substituting the upper and lower limit you get this one, and here you have the natural logarithm of -1, but it is inside the modulus, so it is the same as writing it as natural logarithm of 1, and that is equal to 0, right? Because we have the ln curve like this, and at 1 the ln t will be equal to 0, right? So this is equal to 0. And how about this one? The limit of t goes to 1 from the negative side of t minus 1. What will happen to that? Once again, you can see the diagram of ln curve, right? Now, this diagram says, now if I draw it more clearly, it will be like this. Okay, so you can see when the value of this domain of the logarithm function reaches 0, the function value will go to negative infinity. Okay, when it reaches 0, the function value will go to negative infinity. In other words, the answer for this limit problem will be equal to negative infinity. Okay, now remember, ln function is not defined for negative values, right? That's one of the reasons for having a modulus sign. So it guarantees that always you have the domain as a positive number, right? Okay, so anyway, we have a negative infinity as the answer. That means this integral diverges. Now remember, I said in order to compute the original integral, that is 0 to 3, we need to have the values for 0 to 1 integral and then 1 to 3 integral. And if both these integrals converges, then we can say that this is convergent, and the answer for the integral is the addition of the two integrals. But if at least one of these two diverges, then we don't even have to compute the remaining integral. We can directly say that the total integral will also diverge. Okay, so that's what happened in our example. When we compute the integral by having the left hand point, it has an answer of negative infinity. That means this diverges, therefore the total integral will also diverge, so we don't even have to compute this one. But anyway, you can try and see what as an exercise, you can try to evaluate this integral as well.